record this. And so we're just going to work out some examples, and I'm going to do some very, very simple examples to start with, and then maybe we'll get a little more complicated. And so I'm actually in the book on chapter 14, which is called The Basic Elements and Phasors. And I'm just going to work out some problems in the back of the book. All right. And so if you guys need to, feel you need practice or whatever, I mean, the back of the book has lots of different circuits and stuff to work with. So I'm just going to kind of start off real simple here with problem number 32. And then we'll just work on some other problems after that then. All right, so this is problem number 32. And so looking at this, we see that we have the sine wave. We have this is our voltage source here. And this voltage source then they give us up at the top in the instructions, they tell us what that is exactly. And so it is E. So remember, they're using lowercase e. And technically, I prefer to actually kind of write it as E of t as a kind of a function here. Because it's a time domain function. So this is the time domain function, and this is interesting. They actually have 120 volts peak here. They didn't put the volts there, but sine, and then the sine is 2 pi 60. Okay, so the sine, it's 2 pi 60 times t plus an angle of 20 degrees. And as I mentioned in the last video, I think they like to in the book he likes to make the voltage not zero, which to me it's the voltage should be your reference point because it's what's driving your current. And so I like to shift it to be zero, but it doesn't really matter what it is. You just have to kind of work with it. Now, I do want to point out here, that this is the time domain representation. And what we want to do then is really, when we're going to be calculating currents and voltages and all that kind of stuff, we really want to go to the phasor domain. So in the phasor domain, I would make this like a capital E with a underline to indicate that this is a phasor. And so to go to a phasor, what we do is we take the voltage. All right, now this is the peak voltage because it's a sine wave, so we take that and divide that by the square root of 2. Okay, so 120 volts divided by the square root of 2 at an angle of 20 degrees. Okay, and again, if we were going to put that into Blackboard, we would go ahead and convert this into a decimal representation. So that would actually be 84.853 volts volts at an angle of 20 degrees. And so in blackboard then, to put this into blackboard, I need 3 significant digits. So I need these 3 digits, but because I have the 5, I need to round that up. So I would have 84.9 volts at an angle of 20.0 degrees. Okay, so that's how we want to write that. And so this would be actually my blackboard representation. And a lot of times in blackboard, I actually try to make it a little bit easier for you, and I just maybe have you put in the views, and I give you some of the formatting and that sort of thing. So just pay attention. And again, if you have any questions as you're doing the homework, how should I type this in? Feel free to contact me, and we can go over that. So this is our voltage in the phasor domain. And remember that this 120, all right, this 120 divided by the square root of 2, this is what we call the RMS, root mean square, or the DC equivalent, or the effective value of the voltage. Okay, so this is our AC waveform, and in the time domain form up here, and this is in the phasor form. Okay, now when you are going to do the actual calculations, you really want to make sure that you use like 5 significant digits. Okay, so don't use the rounded up value when you're trying to like calculate currents and things, because especially when you start calculating power, and you start basically squaring values or something, it will really mess up your rounding if you don't take it out to like at least 5 digits. Okay, so I mean you'll basically get the right answer, but you'll have some round off error. But if you take it out to 5 digits as you're doing calculations, and then only round it as you're entering it into blackboard. Okay. All right, so here we have the sine wave, and we're using that to drive a current through a 6-kilo ohm resistor. So let me make a couple of points here about resistors. Resistors in an AC circuit. The voltage is always in phase with the current. Okay, so the voltage is always in phase with the current in a resistor. Okay, we're talking about just a resistor here. Okay, just a resistor, the voltage is always in phase. And so and then this is really kind of the same thing, but it's so what's going to happen is that so if your voltage is at plus 20 degrees, okay, so so whatever angle that is, that's the same. The other thing is, of course, Ohm's law. Ohm's law always applies. Okay, and so we get when we do Ohm's law, right, in DC, remember in DC circuits, Ohm's law basically stated that the current I, the DC current, is equal to the DC voltage divided by the resistance. So in AC, we're using phasors, so it would be I with like an underscore is equal to E divided by Z, which remember Z is the impedance. Okay, Z is the impedance, and the impedance is kind of is defined basically as being R minus X of minus J times X of L, which is the inductive reactance, minus J times X of C. And a lot of times we write that as R plus plus J, X of L, in parentheses, minus X of C. Okay, so, you know, that's all the same thing there, really. But this is, you know, this is the impedance, but in this circuit, all I have is R, right? So all this other stuff just goes away, okay? So, okay, so our impedance is just resistance in this case, okay? So the impedance is simply that. So our current I in the Phasor domain, all right? So I in the Phasor domain is equal to E divided by R, because that's all we have is this resistance. And so we have our 84.853 divided by R, which was 6.8. Okay, and the angle then of the resistance is 0 degrees, but the angle of the voltage was plus 20 degrees. And so our current I in the Phasor domain, that was 6.8K. Okay. 6.8K. All right, so this was a K, 6.8K. Now, one of the things I do when I'm dealing with kilo ohms for impedances is just if I have K here, then, you know, 1 over K is going to give me milli. So I don't actually punch into the calculator 6.8 e to the plus 3. I just change, I just remember if this is K, it's going to give me a milli. And so my answer then is going to be 12.478, and it's milliamperes. And we have the plus 20 degrees minus 0 degrees is simply going to give me plus 20 degrees. So that angle did not change. And again, if I'm plus 20 degrees. And so now if I'm going to put this into Blackboard, I would put 12 point, the 7 would round up the 4, 12.5 milliamperes at an angle of plus 20.0 degrees. Okay. All right, so this again is the Phasor domain current. And the if you wanted to, you could actually do it in time domain, okay? But we don't do that very often, but you can actually, you know, calculate it using Ohm's law and just keep the sine wave there. Okay? So the time domain, we would just put like I of t is equal to E of t divided by R, so that's going to be this sine wave, so that's going to be 120 volts. Okay. Sine, okay, and remember 2 pi 60 is 177 rads per second. Okay, if you multiply it out, times t plus the 20 degrees, And so we could write that then divided by R, which was 6.8K. And so we can we would get that to be 17.647 milliamperes at a sine times sine 377 period rads per second times t plus the 20 degrees. And so if I'm going to put that into blackboard, right, I would be 17.6. Now this 4 would not round that up, so it'd be 17.6 milliamperes sine 377. And I recommend you go ahead and put the decimal point. I'll never mark it wrong for having the decimal point there, even though technically I would also accept in this case, since it doesn't end with a 0, I would accept it just as 377. And I like to put the units there. This is radians per second, and then the 20 degrees at 3 significant digits should be 20.0 degrees. Okay, and so that's kind of how we would want to put that in blackboard. All right, so the the voltage inside of a resistor, the voltage and the current are both in phase. Okay, so those are both in phase there. And so if I was trying to draw this, I'm going to make a little bit of room here and try to draw this So if I wanted to draw this sine wave, okay, so my voltage waveform E would be right here at plus 20 degrees, and it would go up, and of course down. And so this peak value here is, this is E of t, and so the peak value is 120 volts. Okay. And then if I wanted to draw the current, okay, the current is also at plus 20 degrees. And so this is my current I of t. And of course it's at 17, its peak is 17.6 milliamperes. All right, but one of the things to note here is that with these, they both start at the same point. They right here where they cross 0 and return to 0, everything is exactly the same. All right, so we have the we have the sine wave. I drew the sine waves there just so that you can kind of go back the other way and kind of see that. So those two are right on top of each other. The magnitudes are different, but the sine waves are in sync. There's no phase shift there. And so that was the very simple case because it was just a resistor. So with resistances, oh, that was the other point I wanted to make sure I made there, is that with resistances here, I don't know if this is second or third point here, but I deleted the one. But the other point to make here is just that with resistances, it doesn't matter what frequency. Okay, frequency of the sine wave. So remember, our frequency in this case was actually a 60 hertz sine wave. The frequency has, I'm going to say, very little effect on resistance. Okay, and the reason I say that, and I know he talks about it in the book, I forget exactly which chapter he talks about it, but there is something with AC circuits called the skin effect. Okay, and what that means is that if you think about a piece of copper wire or any kind of wire, whatever it's made out of. And so if you have this piece of copper wire, you have all this material inside of here, right? All of this inside of here is theoretically room for current to flow. However, AC circuits tend to gravitate, the current tends to gravitate on the outside of the thing. The current doesn't like to go in the center for an AC circuit. DC doesn't care. DC would like use the entire cable, use all the area inside here for current flow. But AC tends to gravitate toward the outside layers of the wire. It's what, again, it's what they call the skin effect. And as the frequency goes up, it becomes more pronounced. All right. So there is a little bit of difference as the frequency changes, but it's very, very slight until you really start getting up in frequencies. When you start getting, you know, up there into like gigahertz frequencies and things like that, it becomes much more pronounced. But at, you know, at 60 hertz or 50 hertz, which we use for power, right? We use 60 hertz here in the United States, and Europe and a lot of other countries actually use 50 hertz. That's a real low frequency, and the skin effect isn't that big of a deal. Okay. But as you start increasing the frequency, the skin effect will kind of play into that, and so the resistance in the wire and the resistance in, you know, your other elements, it will have a bit of an effect on that. Okay, so anyhow, so that was a simple resistor circuit. And so now I want to, you know, just basically do another one here with a different element. Okay, so if we go and we look at problem number 34, so in problem number 34 here, we have a capacitor. Okay, and so with the capacitor, they give us, it's a 1200 picofarad capacitor, and they give us the frequency up here. So they're giving us our frequency, right? So our frequency F is 500 hertz, and the radian frequency, omega, lowercase omega, is then going to be 2 times pi times 500, which, whatever that is, I guess it's going to be pi, okay? So it's going to be like 314 radians per second or something. Let me just double check that. So 2 times pi times 500 should be, okay, yeah, see, it's a good thing I double checked. So 2 pi times 500 is going to be 3,141.6 rads per second. All right. And so when we calculate X of C, so remember, C is the capacitance of this device. X of C is what we call the reactance. The reactance is the opposition to current flow. Okay, reactance is the opposition to current flow. And the reactance, okay, in a capacitor is defined as being 1 over omega times the capacitance. Okay, and then it also has that minus J term there. It has a phase angle. So a capacitor, in a capacitor, okay, the reactance in a capacitor decreases as the frequency increases. So it's an inverse relationship. It's a 1 over omega C, okay, which is also remember, omega is 1 over 2 pi f times C, okay? So the capacitive reactance in this term is minus J, and then 1 over 3141.6 times 1200 e to the minus 12. Picofarad. Okay, I just had to type that in a couple of times. So, all right, so that is 1 over this 2 times pi times 500 times 1200 times 10 to the minus 12. Okay, and if I punch that in correctly, okay, so if I punch that in correctly, that gives me 265.258. I'm just going to go ahead and write 6 digits for right now. 265.258 ohms, right, with an angle of minus 90 degrees. So this would be the polar form of the impedance. Okay, so this is the polar form of the impedance. And so if we wanted to calculate our current, I, so if we wanted to calculate the current I, I'm sorry, I didn't even read. You know, you should always go back and read the problem. Oops, somehow I got that white. You should always come back up and read the problem. They were giving us the current. Okay, so they are giving us the current up here. They are not giving us the voltage. I just assumed that they were giving us the voltage. Okay, but they did not. Okay. So they're giving us the current, so we have to find the voltage. So the voltage E, and again, I really prefer to go ahead and put E of t there. So the voltage E is I of t. If we're writing it in time domain form, it would be I of t times Z, which is the impedance, which is I of t times minus J, you need parentheses or something here, minus J times the 265. Well, you know, I guess I'll just write in variables here at the moment. Okay, so it's going to be I, which is going to be 30. Oh, I'm sorry, there was a K up here too. Sorry about that. Okay, that was a kilo ohm. Okay, this up here was kilo ohm. And so it's 30 times 10 to the minus 3 times 265.258 times 10 to the plus 3. Okay. And but there's the angle here. So this this one is going to have an angle of minus 20 degrees. Okay. So there's minus, I really like to do these not in the time domain. I really prefer to actually to do it in there in the phasor domain. And then we can always take it back to that. Okay, so it's just when you're dealing with angles, it's clumsy to use the sine wave. So so let's take I and convert it to the phasor domain first. So I have I of t. All right, I'm going to convert that. That's the time domain. I'm going to convert that into the phasor domain. So I get I is equal to, you know, the 30 milliamperes is what it was at an angle of minus 20 degrees divided by the square root of 2 to get into the phasor. Okay, so we divide that by the square root of 2 to get into the phasor. So now, if I want to calculate the voltage in phasor form, so if I want to calculate the voltage in phasor form, that would be E in phasor form is Ohm's law, I times Z. Okay, where remember Z, let me write it down again, just as reinforcement. Z is equal to R plus J x of L minus J x of C, right? But in this case, we have is a capacitor. We have nothing else, so we're just looking at this part. And so we're going to have 30 milliamperes at an angle of minus 20 degrees divided by the square root of 2 times times 265.258 kilo ohms at an angle of minus 90 degrees. So it's at an angle of minus 90 degrees. And so when we do that calculation then, okay, we will have 30 times 265.258. And again, this is milli. Okay, so the milli cancels with the kilo, right? So those kind of just, if you have milli here and kilo here, you can just take the 30 times the 265 divided by the square root of 2. Okay. Or, you know, you can, if you want to punch it into your calculator or your Octave software, you could put in something like 30e to the minus 3, right, times 265.258 times e to the plus 3, and then divide by the square root of 2, right? And you could punch it in that way. But if I got milli for current and I get kilo for resistance, those two just are a wash. So I don't punch the e to the minus 3 stuff into the calculator myself. But if you're, you know, if you're not comfortable with that cancellation, go ahead and put it in there so that you don't make a mistake. So let me finish punching it in my calculator here. I'm just using the Octave software. Square root of 2, and that gives me that gives me 5,627 volts. And look at the angles. Now remember, when you're multiplying phasor angles here, they do a lot of this in the book. When you're multiplying this, then the angles add. So when you're multiplying, angles add. When you're dividing, angles subtract. So so the angles now are going to be a minus 20 minus plus a minus 90. Right, and so the angle is going to be minus 110 degrees. Okay, and so again, if we were going to put that into blackboard, I would write it as 5.63 kilovolts at an angle of minus 110, and I must put the decimal point here. It's very critical because of that 0. It tells me that these, all 3 digits here in this value are important. And so it's 5.63 kilovolts. Okay. Now that's in the phasor form, so if we wanted to write that E of t, because up here they're asking us to write it in terms of E of t, and so if we write that in terms of E of t, we're going to get the 5626. I'm going to just write the 4 significant digits there out for right now. 462 times the square root of 2 volts times sine of 2 times pi times 500, writing it that the way they wrote it, t minus 110 degrees. Okay, and so then if we actually did that math, then I get 7957.7 for 5 digits, volts, sine 2 pi 500. And actually, I calculated that up here. So if I'm going to do Blackboard, I'm going to have to write that out. So we'll put that as 3141.6 T minus the 110 degrees. And so again, if I want to put this into Blackboard, I would be putting in 7.96 kilovolts times sine 3.14 kilorads per second. Radians, I said rads. A lot of times we say rads, but technically it's radians. Minus 110 degrees. And so this would be the Blackboard correct form to put that in. Any questions about that? And if I wanted to draw these waveforms, okay, so if we came over here and we wanted to draw the waveforms, I'll draw the current first. So here is my current, and the current is minus 20 degrees. So that means right here we're going to be at minus 20 degrees. And so the sine wave is going to be coming up like this at minus 20 degrees. And then if we draw the voltage waveform, the voltage waveform is minus 110. All right. And so if this is minus 20, this peak right here is 90 degrees. So if we're measuring this in degrees, this is 90 degrees. And so the voltage waveform is 90 degrees out of phase. So this is the voltage here, all right? And of course the voltage's peak is 7.96K. Kilovolts, and the current peak, they're not the same. They're not even the same units, let alone the same scale here, right? So, but current was 30.0 milliamperes was the peak for that. Okay. All right, now one other thing that they talked about up here was what is the average power? And I didn't even look on the other problem whether they were asking this, because we haven't really discussed power in AC circuits yet. We did talk about how the peak, the power is when you do the phasors, we use the effective value for the voltage in the phasors. Okay. So, but let me just kind of talk about this. I mean, there's a whole chapter on power in here for this, but you know, and I forget exactly which chapter it is, but coming up here not too far away is a whole chapter on power. But just to kind of address that on here, power, we have something called real power. Real power is the power that is being used. Okay, so we already talked about like resistors. Resistors take electrical energy and turn that into heat, right? And they turn it into heat, or technically it's thermal energy. So they take electrical energy and turn it into thermal energy, And so once it's in thermal energy, as far as the electrical circuit is considered, it's gone, right? The energy is still there, but it has been converted from the electrical form to the thermal form, and so therefore it's not really in the circuit anymore, right? It's actually radiating out, right? We can tell this as we, if you walk up to a heater or even a light bulb, and you put your hand near the light bulb, don't touch it, but put it near it, and you can feel the heat from that light bulb, and that's due to the resistance inside of the light bulb, right? So the old incandescent bulbs, even an old incandescent 40-watt bulb, if it was turned on for more than a minute and you walked over and actually touched it, you could get a very nasty burn. Nowadays, we're using mainly LEDs or the fluorescents or whatever, but if you might be able to get away. Most LEDs anyhow, they only, depending on the size of them, they only use maybe 10 or 12 watts. Some of the bigger ones, I just bought one the other day that's like a really big one, and it's supposed to use 60 watts, but it has lots of heat sinks on it to spread out that heat. All right, but the old incandescent bulbs, boy, if you'd touch them, you would get a nasty burns, because you have all that heat there, that all that electrical energy, a lot of it, the light, it's giving off light, and that is actually another form of transferring that energy, but some of it's being turned into heat. Okay. All right, so real power, therefore, we calculate that in a DC circuit. We just said, well, power is equal to the voltage times the resistance. But in AC circuits, we have to take into account that these things are out of phase. And we also have to take in the fact that we want to use the effective or the DC equivalent, which is also the RMS. Okay, so effective power. All right. And so this is the real effective power. So what we would do to calculate power in an AC circuit, the first thing is we have to use the RMS values. So we do voltage RMS times current RMS, but remember, these things are out of phase. Okay, so these things are also out of phase, so we have to track the phase shift. So we have to, we take the cosine of the phase angle, not this phase angle, not this 20 degrees here, not this 110 degrees here. We're taking the phase angle between the angle of the current and the angle of the voltage. And inside a capacitor, that angle is 90 degrees. Okay, and so if you take the cosine, of 90 degrees, you're going to find out that that is 0. Okay, the cosine of 90 degrees is 0. So in that case, we don't even know what VRMS or IRMS are. All right, so if we come up here and say, well, what is the average power loss in a capacitor? The answer is 0. Okay, and so if we wanted to put it in blackboard, it would be 0.00 watts. Okay, that would be the blackboard answer. All right, so the all right, but let's take a look at this equation here for a minute. So when I do this, we have VRMS, well, remember VRMS is actually V peak divided by the square root of 2. And IRMS is actually I peak divided by the square root of 2. And then, of course, we still have this cosine of theta piece going on here. And so, try to make me a little bit of room over here. So when we go through and do this calculation here, right, square root of 2 times the square root of 2 turns out to be 2. So if you do this, and if you see this and they have this in the book, the real power is equal to V peak times I peak times the cosine of the angle divided by 2. The reason that 2 is there is because the square root of 2 times the square root of 2, right, gives you 2 squared square root, which is simply equal to 2, right? Because you take the square root of something squared and you just left with that. And that's why you can use the peak voltages divided by 2, the peak voltage and the peak current divided by 2, or you can use the RMS because you are using the exact same thing. The peak voltage times the peak current divided by 2 is equal to the RMS values multiplied together. So that's where that comes from. But you have to pay attention to this angle of the voltage and the current. But inside a capacitor, as we discussed before, capacitors store electrical energy inside of an electric field, and then as they're charging, they're storing that energy, and then when you flip the current away and drive it in the opposite direction, they dump that energy back into the circuit. So that energy is being put into the electric field for half of a cycle, and then the other half of the cycle, that energy is being dumped back into the circuit. And so therefore, capacitors do not use electrical energy. They store electrical energy. They don't use it. Okay, so there is no average power loss inside of a capacitor. Okay, because the energy is never leaving the circuit. So any questions about that? All right, so and it's pretty much the same thing. For the see, it's pretty much the same thing there. For an inductor, the only difference is the inductor is storing the energy into a magnetic field for half of the cycle and then dumping it back into the circuit during the other half of the cycle. So inductors and capacitors do not lose power. Okay, the power stays inside of the circuit. Again, for half of the circuit, that energy is dumped into a magnetic field for an inductor, but during the other half of the cycle, the inductor takes it out of the magnetic field and puts it back in the circuit. So the average power lost within the circuit for inductors or capacitors is 0. Okay, they do not use energy. Only resistors or semiconductor devices, which are basically resistive devices, or like light bulbs are effectively resistive kind of things. Those things are using power. They're taking it out of the circuit and converting it to heat or light, or case of electric motors, into mechanical energy. But Capacitors only store the energy and dump it back into the circuit. Inductors store the energy and dump it back into the circuit. Yes, I will be having an industrial robotics lecture at 12 o'clock. All right, so now one other thing though, talking about this energy loss, the inductors have a bunch, remember that inductors are made up of a bunch of big coils of wire. And since they're made up of coils of wire, they do in fact lose energy, okay? But officially, the energy that inductors lose isn't due to the inductor, but they're due to the resistance inside of that copper wire. So when I say that inductors have no average power loss, I'm talking about the ideal inductor, and I'm ignoring the resistance in the circuit. So inductors do heat up, because they have all that resistance inside of all that copper wire. So inductors will heat up and convert that electrical energy into thermal energy, but it's the resistance inside of the wire that's doing that. It's not the inductive property of the inductor. It's the resistive property of the copper wire we use to build it. Now, capacitors, they're pretty much ideal. They don't get hot normally. If you got a capacitor getting hot, that means it's actually leaking current. The current is somehow sneaking through that dielectric, and it's not supposed to, which means your capacitor is bad. All right, so capacitors really don't heat up. They might get just a tad warm, because the plates on them and the metal leads going into them do have some resistance, but they don't have nearly as much resistance as like an inductor. So capacitors in general don't really heat up. They are not going to lose any energy through there, but inductors will lose energy, but again, it's just due to the resistance in the wires. All right, so I could do the same kind of simple circuit like this for an inductor. All right, and the only difference is if this was an inductor, let me just take this circuit and say, if this circuit was an inductor instead of a capacitor, the only difference is that X of L would be calculated using 2 times pi times omega times L instead of this 1 over equation, okay? And so that it would have a plus 90 degrees here. So it would have a plus 90 degrees if it was an inductor. And so down here where we had minus 20 degrees and then plus a minus 90 before, but now we're going to have a plus 90. And so my angle, if this was an inductor, my angle would be plus 70 degrees. Okay, so my angle for my voltage would be plus 70 degrees. Because remember Eli the Iceman? Right? Inside of an inductor, the voltage is ahead. But inside of a capacitor, the current is ahead. Okay, and so, you could do basically this entire same circuit, but X of L is going to be a lot different. Okay, so remember here, this was 1200 picofarads, so the this was 265 kilo ohms here. So that was 265 kilo ohms. And then, but if we actually calculated this one, let's see if I can find some room here, just to show you the huge difference. Okay, so if we took that this was actually an inductor, and the inductor was 1200. Okay, so if it was an inductor, and the inductor therefore would be 1200 picohenries. Okay, then the inductive reactance, okay, remember it'd be a plus J, which, remember, the plus J means plus 90 degrees. Okay, plus J times 2 times pi times 500, right, because that was what was given up here, and times 1200 times pico is 10 to the minus 6. So if we calculated that, we would get all right, so if we calculate that, let me count my zeros here. Well, I'll write it out first, I guess, so we can kind of see it. So it's 0.0000003 7699 is what I calculated that to be. So if I was to write that enter that into Blackboard, all right, it would be J, and then I would have to move this over 3 and move it over 3 more, so it would be 3.77, because this 9 would round that 6 up, 3.77 micro ohms, which is a tiny, tiny, tiny resistance. Okay, so at 500 hertz, this amount of inductance has practically no reactance at all. This is tiny, right? 3.77, right? Look at all these zeros up here. That's just a tiny, tiny value. All right, so any questions related to this here? All right, so let's go ahead and pick a circuit with more than just one element in here. Okay, and please stick with me here. I'm going to close this pane out because it's getting slow. I think what happens is oh shoot, I should have probably changed the thing first. But I think what happens is because I do so much and it's counting dues or something, it just seems to eat up a lot of memory, and then it starts running really slow. So I'm just going to refresh this. Oh, seems to have recalled it. That's cool. I didn't expect that, if that's what it's doing here. Okay. All right, so I was half afraid that Blackboard was going to freak out on me there. So, all right, so let me see if I can find something in here. 55 looks interesting. take a look at 55 here. And, you know, I kind of encourage you, as I mentioned earlier, to, you know, to go to the back of the book or the back of the chapter, the end of every chapter, right? They've got lots of problems. And the actual answers to the odd numbers are in the book. So, you know, go ahead and work out some of those. Of course, for your official homework, some of them I do take right out of the book. Some of them I find from other sources or whatever. But I highly recommend that you go to the end of each chapter and especially work out the odd number ones or even the even number problems if you want. And work those out to you know, so that you can you know, just get some practice, and you can look at the answers at the end of the book, or if you see a problem with an even number that you think looks interesting, go ahead and work it out. And then if you want the answer, contact me. I believe somewhere I do have the solutions to all the questions in the back of the book, and if not, I'll just work it out and get it, and you know, just to to help your understanding. Okay, so you really kind of need to work through these problems until you understand it. And so, you know, the few questions in the homework, if you don't feel like you still have a strong enough understanding, you know, definitely work out some more problems and practice, because that's really how you're going to be comfortable doing this. All right, so let's go ahead and take a look here. This problem is by Kirchhoff's voltage law. Right? So remember that Kirchhoff's voltage law, KVL. Right? So KVL says that the sum of the voltages around a loop are equal to 0. And so they're giving us here En. So they are giving us En. And then they're asking us, they're giving us VB. Okay, they're giving us En and their input voltage. And they're giving us VB. Now remember, these are lowercase because they're giving us the sine wave form of these. Okay. And so E, capital E with an underscore, would be the phasor representation, which is going to be 60 divided by the square root of 2 at an angle of plus 90 degrees. And VB, they're also giving us the voltage here on this box. VB, and VB is 20 divided by the square root of 2 at an angle of minus 45 degrees. And so they are asking us then, what is VA? Well, you know, if we look at KVL, KVL tells us that E plus VA plus VB must equal 0. Okay, so now, but remember the VA is going to be a voltage drop. So look at the signs here. So we're going plus E, and VA is actually going to be a minus. So it's actually going to be a minus there. And VB is going to be a minus because they're drops. Okay, this is a power supply or a source, and these are some sort of drop. Okay, so we'll go ahead and calculate this. I mean, this is a really simple problem, but I'm going to go ahead and find out what is in these boxes. Okay, so I didn't really see them asking us for that, but we're going to go ahead and do it. So we're going to take here, so VA, right, if if you add V to each side, right, you get VA is equal to E minus VB. Technically, these are phasors, so they should have underscores on all of them. And so in phasor form, we had 60 divided by the square root of 2 at an angle of plus 90. That should be a plus sign there, kind of hard to see it. Plus 90. And then we're going to subtract off VB. And so VB was 20 at an angle of, or divided by the square root of 2 at an angle of minus 45. So we need to calculate this. And you could do all the fancy phasor math that they go through in the book. I think half, these couple of chapters here, half of what they're doing is you just showing you all the different algebra to do complex algebra. All right. I'm like, that's fine and dandy and lovely, but why don't we just punch it into our calculators? So I'm going to use the Octave program here, and I'm going to punch this in, and I'll copy what I'm putting in here for you over into the other screen. I don't want to switch because sometimes Blackboard will try to lock up on me. So I'm going to use the Octave software, and so I'm going to take 60 divided by the square root of 2 times, and then I need that angle. So we have to do the angle. So it's E. All right. So we're going to do E. Let's see. Sorry. So when I put this in here, right, and again, if you have a TI-84 and you want to do it in your TI-84, you're going to have to do the same thing. So what we have to do is to put it in the angle of 90 degrees, we would have to put it in as 60 divided by the square root of 2, right, times E to the minus I, or sorry, plus I times 90 degrees times pi divided by 180 degrees. Okay, and you have to put it in like that because when you do this E to the I here, this needs to be in radians, and so the degrees will cancel, and you'll be left with pi radians times 90 divided by 180, which is pi over 2 in this case, but that's just in this particular case. All right, so that's what I'm punching in here. I times 90 times pi divided by 180. And then I'm going to subtract off 20 divided by the square root of 2 times I times E to the minus I times 45 times pi divided by 180. And now I'm getting the answer. Now I'm using the Octave software, so it gives me the answer in the polar form, or in the rectangular form. And so I need to put it in the polar form. Okay, I'm sorry, this is a voltage here. So I'm going to do the polar form. So I need to take the absolute value of it. And then I need to calculate the angle, but again, I'm going to get the angle in radians, so I'm going to have to convert it to degrees. So the angle would be And so let me copy this so you guys can see it then. All right, so here is my calculation inside of the Octave software. So I really tried to spell it out here for you. Okay, so I had 60. So we had 60 divided by the square root of 2 times this e to the minus to the I times 90 times pi divided by 180. All right, and then here's my minus sign here, minus, and then we had the 20 divided by the square root of 2 times e to the minus, because this is a minus up here, okay, to the minus I times 45 times pi divided by the 180. I guess it got cut off over there. Okay, didn't quite make the screen. But that is the thing. Let me see if I can just scroll over if it, yeah, it's almost there. But so this is how I just punched it in. Now again, it gives it to me in rectangular form. And this Octave software, if you don't specify a variable name, which I didn't, what it does is it stores it in a generic variable called answer. And so then what I did was I took that, this is the rectangular form here, right? This is in rectangular form, but I wanted to get it in polar form. So I take it in polar form. I take the absolute value of this, which they walk you through that in the book, but I take the absolute value, and I'm just using this generic answer variable for that, and that gives me the magnitude. So this is 53.4 volts at an angle of plus 1.76 degrees. Okay, so remember, this was VA. This was my voltage VA. All right, so the question then becomes, what is in this box? Okay, the question that I have now is, what is in the box? And let's see, I guess VB. Let's see, we weren't given any current though. I was thinking we had a current, but we aren't actually given a current. So if I don't have a current, I can't apply Ohm's law. So I guess I can't find out what's inside of that box very easily here, because I know the phase shift. I know the phase shifts here, but I don't know the actual current. So Ohm's law, right? Ohm's law is the impedance is the voltage divided by the current. But if I don't have a current, I guess I can't find out what's in the box. All right, so, but anyhow, that's how we would do that. Now, if we wanted to draw the phasor diagrams of these, okay, I can just do that for you fairly quickly. Again, they didn't ask for that, but give you a little bit of practice with that. So if we wanted to draw the phasor diagram, So I just want to make a little room here. So I'm going to draw the phasor diagram. So we have E was going like this. So E software is going slow again. Come on. Okay, so E is going at plus 90 degrees. So E is going this way, and it's going straight up plus 90 degrees. Okay, so this is E, which is 60 divided by the square root of 2 at an angle of plus 90 degrees. This should be a perfect straight angle, but of course it wasn't. Okay. Now, the VA is minus 45 degrees. So it's minus 45 degrees here. Let's see. This should be 7. Hold on. Let me check my values here. Did I calculate that right? Minus E was plus 90. Okay, yeah, I'm sorry. I was like, I knew something was not working there. This 175 was in radians. Okay, so this value here, when I punched it in, not quite sure what I did, but this was still in radians. This value, this number is correct, but this number is 1.75 radians, not degrees. So when I calculate it in degrees, it's 100.8 degrees. I don't know exactly what I did when I tried to calculate it in degrees, but it did not come out correctly. I'm not sure. Oh, I see what I did. Yeah. Yeah, I punched it in the I punched it in there wrong. And so the yeah, okay. So 17593. That's interesting the way I did that. I actually got the correct radians, but this value was in radians, not degrees. So now I can draw it a little bit better. I was a little bit worried there. So now what we have to do here, this is 100 degrees. So that means that this one, this was VA. So VA is going up this way at 53. And this is not to scale, okay, but it's going this way at 53 degrees. And or I'm sorry, not 53 degrees, 53 volts. So this is 53 volts going out this way. Okay, so this was 53 volts going this way. Now, I'm looking at this and it's saying 60, but remember it's 60 divided by the square root of 2. Okay. So, uh, 60 divided by the square root of 2 for a phasor is only 42. Okay, so 60 divided by the square root of 2 turns out to be something like 42.42 volts. Okay, so this here is basically about 42 volts in magnitude. 42 volts. Okay, so this magnitude is 42 volts here. So now if I draw VA, and VA is 53, the magnitude of VA is 53, so it's going to put me up about here somewhere. All right, so this angle is 100.8 is this angle. And so this is VA, and it's about 53.4. And so now if I pick a different color, maybe green, so I'll do VB as in green. VB is 20. So VB, this is VB, which has a magnitude of 20. And the angle right here is the angle we're measuring is minus 45 degrees. And so this is my phasor diagram satisfying Kirchhoff's voltage law. Okay, so remember Kirchhoff's voltage law says that the sum of the voltages must equal 0. And we can draw that physically, and we can sketch that out to see if that makes sense. And I'm glad I did that, because otherwise I wouldn't have realized that this angle is so far off. And again, the angle actually wasn't off. It was just the fact that the angle was in radians and not degrees. Okay, so it was actually the right value. My scaling, I tried to type in, I had a typo in my scaling. You want to do a problem from last week's assignment? Sure. You got any particular one in mind? The sine wave that asks for a list of info. Okay. Sine wave A. Yeah, I started trying to label my pictures and things so that, you know, because when you're scrolling up and down on a computer screen like that to do the homeworks, you know, and you're like, well, the sine wave above or whatever, I think it can be confusing. So I'm trying to like label them and give them names. So sometimes like you might have a sine wave C, even though you didn't have an A or a B, just to let you know on that. But that's why I do that, because those, you know, just as you're scrolling up and down the screen, it's really easy to scroll too far or something and see, oh, well, there's a sine wave. He's talking about that one. So I'm trying to label them and just give them names. And sometimes the names, like I say, it might sound a little off because you're like, oh, well, this is, you know, circuit AQ or whatever, because I just don't want to have like two circuit A's or two sine wave A's on there. So I just kind of label them that way sometimes. So let me open this up and see sine wave A. Oh, okay. So sine wave A, this was actually a picture right out of the book, I believe. And they want us to find, oh, okay, I remember this problem. Yeah, okay, good question. Good question. So here is this sine wave that seems pretty generic. And but I do give you that the time t1 here, the time t1, this value right here, we know what that time is. Okay, so I give you, we know that the peak value is 10, and we know that t1 is 15 milliseconds. So at this point right here, okay, that is 15 milliseconds, and that's the peak. Okay, and you know, sometimes it's really hard to tell there, but that's the peak. So the question is, what is the period? Well, this is, let me change colors here for a minute. Okay, this is one cycle right here, right? So this is one cycle, and then from here to here is a second cycle. But I didn't give you that time, did I? So, but this is half a cycle.
Call from 330940654.
Okay, I'm not answering that one. I don't know who it is. Okay, so the this is right here is one cycle, or one half of a cycle. This is half of a cycle, and this is half of a cycle. Okay, so so if we do the little bit, okay, so this is 1/4 of a cycle. This is 1/4. This is 1/4. This is 1/4, and this is 1/4 of a cycle. And so if this is 15 milliseconds, right? And so if we divide that by 1, 2, 3, 4, 5, okay, so we divide 15 by 5, right? We get 3 milliseconds. So 1/4 of a cycle is taking 3 milliseconds. So that means TA is 3 milliseconds. And then this point here would be 6 milliseconds. And this then would be 9 milliseconds. This would be 12 milliseconds. Okay. And so, and going on, right, this is 15 milliseconds. So this would be 18. And this point would be 21 milliseconds. And 3 more would be 24 milliseconds. And so TB there would be 27 milliseconds. Okay. All right, so everybody with me here so far? So now, all right, so now we can talk about the period, right? If 1/4 of a period is 3 milliseconds, then T is 4 times that, right? Which is 12 milliseconds, which we can see right here. I've got this labeled here. Here's my 12 milliseconds, right? So one full period is 12 milliseconds. All right, and so therefore we can define the frequency as 1 over 12 milliseconds. Which is 83.3, if I calculated it right, 83.3 hertz. And then we can say, well, omega is 2 pi divided by t, which is also 2 pi f, whichever way you want to go. All right, and so omega is 524, and the units for that are radians per second, or I'll just take rads per second. Okay, now actually I gave you all the units here on this problem. So, you know, the units were there. I just asked for you to type in the value. So the value would just be 524. And again, I recommend that you put the period, but I actually have with or without the period is acceptable because it's not ending with a 0. All right. And so now the peak to peak value, okay, the peak value, we're stating that the peak value here is plus 10. So the negative peak is minus 10. So volts peak to peak is 10.0, is the difference here. So V peak to peak is the peak value minus the valley. And so that's 10 minus a minus 10, so that's 20.0 volts. So remember, when you put these in, I'm asking, again, I gave you the unit of V. I gave you the units are already in there for you. So I just am asking for 20.0. That's all I asked there. So if you went ahead and put the volts in there, the capital V for volts, that's okay, but you know, Blackboard's going to mark it wrong, so you have to let me know. Okay. Now the phase angle of the waveform is crossing 0 at 0. So the phase angle is simply 0. Okay. So the phase angle, which I called phi, is simply 0. So that would be 0.00 in Blackboard. But T2, what is T2? Well, T2 is given that the voltage is 6 volts. Okay, so T2, all right, so let's write our sine wave first. So we have, in terms of the time domain, we have V of t is equal to 10 volts times sine of 524 radians per second times t plus no angle. So this is our time domain representation. All right, so the angle is 0. And I want to find out what is it at time t equal 2, but I'm given in the problem, okay, that at t2, at t equal to t2, at t equal to t2, V of t is exactly 6 volts. That was given. All right. And so I said, I'm not sure what T2 is, but I want to know what T2 is when this is 6 volts right here. And so therefore, I stick this in my sine wave equation. So I'm going to say V of t, okay, V of t2, V of t2 is equal to 6.00 volts, which is equal to 10.0 volts sine 524 times T2. Use some square brackets here to just kind of separate those. All right, and so I need to solve for T2. So I have to, first I'll divide both sides by 10. So I get 6 over 10 is equal to sine 524 times T2. And then I'm going to have, I'm going to have to take the arc sine, or the inverse sine. Okay, so I'm going to take the inverse sine, so sine, let's see, I'm running out of room here. Let me resize a minute. Give me a little bit more room to work with. All right, so I'm just going to come down here. So we got 6 over 10 times sine 524 T2. And so now what I need to do is I need to take the inverse sine. So I'm going to do inverse sine, or the arc sine of this is equal to the inverse sine of the sine. And so by doing that, this side, the sines cancel and they're gone. All right, so then I have to take the inverse sine, or the arc sine, of 6 over 10. And then, so this is going to give me sine inverse 6 over 10 is equal to 524 T2, which is going to give me then that T2 is equal to this sine inverse 6 divided by 10 divided by my radian frequency 524. And so if I punch that in my calculator, then I did everything correctly. So I get 1.23 milliseconds. So let me show you how I type that into octave here. Let me copy and paste this over here. Oops. Okay, so when I punched it into octave, lost it. There it is. Right there. I guess I didn't lose it. It was popped in up top there. All right, so make it a little bit bigger here. Okay, so when I punched it into octave, I got I use the A sign. A sign stands for arc sine or sine inverse. 6 divided by 10 divided by radians per second, and that gave me the T2. That gave me here the T2. Waiting for the software again. Okay. So T2 is equal to 1.228 milliseconds, which would become 1.23 milliseconds. Okay, and again, I'm only asking in this problem, I gave you all the units, all I asked for was the value. So now, one thing to double check is that, does that make sense? Well, shoot, I'm gonna have to undo all this here. All right, so remember, looking up here in the problem, in the sine wave, right, this is 0 milliseconds, and this is 3 milliseconds. So T2 has to be somewhere between 0 and 3 milliseconds. So if T2 is equal to 1.23 milliseconds, it's in between 0 and 3 milliseconds, so that definitely sounds like a good answer to me. Okay. So, you know, you can go back and compare your answers and see if they at least sort of make sense. You know, if I would have wound up with something like, you know, 16 milliseconds or, you know, something like that, then it's like, that doesn't make any sense at all. But 1.23, that sounds maybe that's correct. Okay. So that's gives you a good kind of reference point if you kind of go back and look at the graph to determine that. Okay, so you're saying 5 volts gave you 1.5 milliseconds. Well, you just change that equation, just put a 5 in there. And no, for 5, yeah, no, 5 doesn't make sense, because if I get 0.999 milliseconds. If it possible, if the voltage is 5 volts, I get 1.5. I see what you're saying. Yeah. The problem is that the sine wave goes up really fast and then slows down. Okay. So when you look at the sine wave, okay, the sine wave here is rising really, really fast. Let me grab a different color here. Okay. Right along here, the sine wave is going up really, really fast. And then here, it's slowing down. Okay, so it's not linear. So what you're saying is, you're saying, hey, if it goes from here to here, you know, I'm drawing over here because it's so messy over there. But you're saying that, hey, if I knew that this distance was 3 milliseconds, and if I wanted 5 volts, which would be halfway, it would be 1.5 milliseconds. Okay, I believe that's what you're kind of saying that you did logically. Well, the problem is that, see, it went up really, really fast here. It didn't go up in a linear fashion. Sine waves are not linear. And so, you know, that's where that logic fails, is because it's not linear. Okay. All right, because it's going up really, really fast here, but see right here, it really slows down. Okay, so it's actually reaching 6 volts in less than, right? It's reaching 6 volts, or it's reaching 5 volts. It's reaching 5 volts in about 1 second. all right, or 1.0, actually it's 999. It's reaching it just under 1 millisecond. It's 0.999 milliseconds. Okay, so it's just under 1 millisecond, not 1.5 milliseconds, because it's going up very fast and then it slows down. So it's not linear. Okay. All right. So remember, you need to go back and look over your homework. And if you miss something, try to figure out why you missed it and see if you can figure it out. You really need to do that yourself. But then if you can't figure it out, then be sure to contact me and I'll be glad to work through the problem with you.